So I will speak about an object called the amplituhedron, and I'll tell you about a series of joint works with many co-authors, including Evan Zohar, Stephen Karp, Zvika Leckrec, Matteo Parisi, Melissa Sherman Bennett, Ron Tessler, and Yan Zhang. So here's an overview of what I'm going to tell you about. I'm going to start by telling you what is this object called the positive Grassmannian. And then I'll tell you about scattering amplitudes and this geometric object called the amplituhedron. Then I'll explain that to understand the amplituhedron, we try to triangulate or tile it. And then I'll explain how these tiles are connected to cluster algebras. And then at the end, I'll tell you about a kind of cool numerical conjecture called the magic number conjecture. And along the way, I'll show connections to nice objects from combinatorics, including cyclic polytopes, Neriana numbers, and plane partitions. And please feel free to interrupt at any point if you have a question. Okay, so let me give a little bit of background on the Grassmannian and its matroid stratification. So the Grassmannian is the set of k-dimensional subspaces of an n-dimensional vector space. And we will represent elements of the Grassmannian by full rank k by n matrices, and the row span gives us the k-dimensional subspace. And just a reminder, Plücker coordinates are very useful in this context. So if I is a k-element subset of the numbers 1 through n, then the Plücker coordinate p sub I of c is the minor, it's the determinant of the k by k submatrix of c located in the columns I. So these Plücker coordinates give us an embedding of the Grassmannian into projective space. And now there's an object called a matroid associated to elements in the Grassmannian. And the matroid I will define in terms of bases. So concretely, if you give me a full rank k by n matrix C, then the matroid associated to C will be exactly the k element subsets of 1 through n, where the corresponding Plücker coordinate is non-zero. So in other words, if I think of my k by n matrix as a collection of n columns, then this matroid is recording which columns form a basis. Okay, so back in 1987, Gelfand, Goreski, McPherson, and Serganova introduced the matroid stratification of the Grassmannian. And so given script m, a collection of k element subsets of 1 through n, we will let S sub m be the set of elements in the Grassmannian where your Plücker coordinate p sub I is non-zero if and only if I belongs to that collection. So this is called a matroid stratum. And the matroid stratification is the decomposition of the Grassmannian into these matroid strata. Now, this stratification has a lot of very nice properties, but the topology is terrible, as was proven by Mignoff's universality theorem. So he showed that the topology of a given stratum can be as bad as that of any algebraic variety, and this led to some interesting follow-up works, like a paper of Ravi Vakil called Murphy's Law in Algebraic Geometry. Anyway, so, okay, the main takeaway is that these matroid strata have bad topology. Now, on the other hand, if you throw in the adjective positive, everything becomes extremely nice. Okay, so this dates back to work of Lustig in 1994. So he created this theory of total positivity for real reductive groups and partial flag varieties. And this was subsequently studied by Constance Reach, and then by Alex Postnikov. And in particular, Postnikov wrote this very influential preprint on the totally non-negative or positive Grassmannian. Okay, so what is that object? Well, the TNN Grassmannian, which I'll sometimes just call positive Grassmannian, is the subset of the real Grassmannian where all Plücker coordinates are simultaneously non-negative. Okay, now really they're just defined as coordinates on projective space, so to be very precise, I could just say all Plücker coordinates have the same sign. And now, inspired by the matroid stratification, we can say, okay, we want to, again, partition the Tiannin-Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are 0. So just as before, let's let script M be a collection of k element subsets of 1 through n. And we'll let S sub m be the subset of the Tiannin-Grassmannian, where your Plücker coordinate is strictly positive if and only if I belongs to the collection. Okay, and then otherwise, since we're in the totally non-negative part, your Plücker coordinate must be 0. And now, in contrast to the terrible topology of matroid strata, these strata are actually cells. They're homeomorphic to open balls. So, so this gives us a cell decomposition called the positroid cell decomposition of the Tiannin-Grassmannian. And in Postnikov's 2006 preprint, he classified which collections M give rise to a non-empty stratum, and showed that these strata were cells. And you can completely classify these cells, and they're in bijection with various combinatorial objects. Okay. So anyway, so this is completely understood and extremely nice combinatorially. Okay. All right. So so I'll just mention that in my own life, I've seen connections to the Tiannin-Grassmannian, to sort of quote-unquote real life. So, so back in 2006 with Corteil, we made a connection between the combinatorics of cells of the Tiannin-Grassmannian and the stationary distribution of a one-dimensional lattice model. You have particles hopping and repelling each other on a one-dimensional lattice, and for some reason you can understand the stationary distribution of this asymmetric simple exclusion process in terms of the same combinatorics that classifies cells. And then in some years later with Kodama, we made a precise connection between the cell structure of the Tiannin-Grassmannian and regular soliton solutions to the KP equation, which has to do with shallow water waves. But then the story that I want to focus on for today dates back to 2012 work of Arkani Hamed, Borgeli, Cachazo, Gontroff, Postnikov, and Drinka, in which they first realized that you can use the Tiannin-Grassmannian to compute scattering amplitudes in n equals 4 super Yang-Mills. So this has to do with scattering of elementary particles. Okay, all right, so just at a bird's eye view, what are scattering amplitudes? So the scattering amplitude is a kind of probability amplitude that describes what happens when some particles with given momenta collide. And this scattering amplitude is actually the fundamental quantity of interest in scattering experiments, for example, at the Large Hadron Collider. And you can compute these scattering amplitudes in different quantum field theories. The one relevant to today's talk is n equals 4 super Yang-Mills, which I understand to be a toy model of a toy model. But anyway, it's mathematically very, very beautiful. Okay, so now I want to actually define this geometric object, the amplituhedron. And so this was defined by Nima Arkani Hamed and Yaroslav Trinka in 2013. Okay, so first I just give you the definition. So the amplituhedron depends on a choice of 3 positive numbers, n, k, and m. K plus m is at most n. And it also depends on a choice of matrix Z. So Z is going to be an n by k plus m matrix. And we're going to require that its maximal minors are positive. So you choose any k plus m rows of this matrix, and the corresponding determinant must be positive. And now Z tilde is going to be a map. So I'll just write it down. It's going to be a map from the positive Grassmannian to the Grassmannian of k-planes and k plus m space. And this map is just matrix multiplication. So we take a K by N matrix C representing a point of the Grassmannian, and we're just going to multiply C times Z, and this matrix is a K by K plus M matrix. And one can check using the fact that maximal minors of Z are positive, that this matrix has full rank and hence represents a point in this Grassmannian. Okay, so this is the map Z tilde. And now the amplituhedron is the image of the positive Grassmannian under this map. So it's a subset. It's a full dimensional subset of the Grassmannian of K-planes in K plus M space. Okay, so why would one define such an object? So, okay, so this is how they came to it. So the probably the most important tool in this area was this famous recurrence of Brito, Cacciazzo, Fang, and Witten expressing scattering amplitudes as sums of rational functions of momenta. And the output of this recurrence, you know, is this sum of rational functions, and individual terms had spurious poles, so singularities that are not present when you sum everything up. And then in 2009, Andrew Hodges observed that in some cases, you can interpret this amplitude as the volume of a polytope. And the spurious poles arise from internal boundaries of a triangulation. So just to draw a kind of cartoon picture, here's a polytope, and the amplitude can be expressed as a sum of 3 different terms corresponding to these triangles, and each term has a has poles coming from these boundaries, but the 3 terms included some spurious poles, namely factors corresponding to these internal diagonals, and they disappeared when you summed everything up. Okay. So Hodges asked, in general, can you interpret this amplitude as the volume of some geometric object in such a way that the BCFW recurrence is exactly corresponding to ways of cutting up this geometric object? Okay, so that was the question that Arkhani Hamed and Trinka answered when they defined the amplituhedron. I mean, of course, they gave this beautiful answer, but the fact that it had these properties was conjectural. Okay, and the BCFW recurrence, as I said, gets interpreted as a kind of triangulation or tiling of the m equals 4 amplituhedron. So m equals 4 is the parameter that makes is most relevant to the physics, but the amplituhedron makes sense for any m.
This amplituhedron sits in Grassmannian, not in the vector space.
That's right. It sits in the Grassmannian. It's a subset of the Grassmannian.
Since it's a polytope.
It's not a polytope. So in fact, their name is terrible. It's not a polytope. Amplituhedron sounds like it's a polytope. It's not a polytope, except in some very special cases, like when k equals 1, then you can think of it as a polytope. Yeah.
But it's still open in the Grassmannian, right?
It's closed.
Oh,
it's closed.
It's closed.
Yeah.
So it has a boundary, a well-defined boundary.
Yes. Yes. Although even the complete description of the boundary is somewhat conjectural. Yeah. Okay. All right. So this is where the motivation came from. And just to say a tiny bit about the physical connections, the m equals 4 amplituhedron encodes the geometry of tree-level scattering amplitudes in planar n equals 4 super Yang-Mills. And there are also physics connections for m equals 2 related to the MHV sector. Yeah, okay. So m equals 2 and m equals 4 are most relevant to physics, but the amplituhedron makes sense for any m.
So, quick question. Your definition, the amplituhedron depends on this matrix Z.
That's right.
But then as we go on, it stops depending on
that's because I was a little bit sloppy if I dropped it. Yeah, so I drop it in some places. That's right. That's right. It does depend on Z. And in fact, many properties seem to not depend on Z. So pretty much all the results that I'll talk about today do not depend on the choice of Z, but of course the definition itself depends on Z. Yeah.
4 is kind of tree level, 2 is correction. The next one should be M0 or whatever.
So m equals 4 is tree level, but there's also a definition of loop amplitude-hedron which is still m equals 4, but is more complicated.
So M6 also appears here in calculation.
So we do not know of a physical interpretation to m equals 6. Yeah. Okay. All right. Anyway, the amplitude-hedron got a lot of popular press. It was called a jewel at the heart of quantum physics. Number 10 among the 100 top stories of 2013. It was one of the 25 best inventions of the year 2013. I don't know how they managed to get this kind of publicity, but maybe mathematicians should try to do the same. And these pictures too. Like, I have no idea how the artist came up with, decided on this kind of picture, but
it looks like Calabi pictures, which has nothing to do with Calabi.
Yeah. Yeah. Okay. So so I want to give you a little bit of intuition for how to think about the amplitude-hedron. So let me take some special cases. So first, if m equals n minus k, then Z is a square matrix, and this map is invertible, and essentially the amplitude-hedron just recovers the positive Grassmannian. Okay, so that's a bit boring. The next interesting case is k equals 1 and m equals 2. In this case, our amplitude-hedron will sit in the Grassmannian of 1 planes in 3 space, which is P2. And in this case, the amplitude-hedron really just recovers a polygon. Okay, so how can we see that? So let's write Z. This is now an n by 3 matrix with positive maximal minors. Let's write it as a list of rows. And each of those rows represents a point in P2. And the fact that maximal minors are positive means that there's a cyclic ordering on those points in P2. Okay, so we can draw this picture right here. And then our map Z tilde. So this map here is going to take our matrix C, which is a 1 by 3 matrix, to the product CZ. And this is just going to map C1 through Cn. Oh, well, that should be C1 through C3 to this linear combination of the Z's. So as Ci's range over non-negative real numbers, we get points in this polygon in P2. Okay, so here we do have a polytope. And in general, for k equals 1, we do get a polytope. We get a polytope called the cyclic polytope in RPM. Any questions? Okay. All right. M equals 1 is also a very nice concrete case, and in this case, your amplitude-hedron lies in the Grassmannian of k-planes in k+1 space, and it turns out to be homeomorphic to the bounded complex of a cyclic hyperplane arrangement. So that was work that we did with my former student, Stephen Karp. And so here are some pictures. Given your Z matrix, you can write down a certain hyperplane arrangement. Hyperplane arrangement is cutting space into regions, and you just look at the bounded regions and the union of those, and that winds up being homeomorphic to the amplitude-hedron. So it's not convex anymore, but it's still sort of polytope-like. Okay, in general, we believe the amplitude-hedron is homeomorphic to a ball, and this is true for m equals 1, and it's also true for some special Z. Okay, so how can we understand the amplitude-hedron? Well, going back to the original motivation, we want to understand its volume, so we want to triangulate or tile it. So physicists were talking about triangulations, but of course we don't actually have anything that's a polytope, don't have simplices, so we prefer the word tile. But I have to tell you what should be the right notion of tile and tiling. So we want an analog of triangulation of a polytope, but now for this non-polytopal object. Okay, so this is just a reminder of the definition of amplitude-hedron. And as I said before, it is full dimensional in the Grassmannian of k-planes in k+m space. Okay, so we define, so the amplitude has been defined to be the image of the positive Grassmannian under this map. And this positive Grassmannian has dimension k times n minus k, which in general is bigger than the dimension of this Grassmannian. And so we have this surjective map from the TNN Grassmannian onto the amplitude. Okay, so what we want to do is cut up the amplitude over here using images of cells here. Right? We had this very nice cell decomposition of the TNN Grassmannian. We have cells of all dimension. So what we want to do is take correct dimensional cells of the TNN Grassmannian and use their images to cut up the amplitude into pieces. Okay, so we're going to define a tile of the amplitude to be the image of a km dimensional cell such that the restriction of z tilde to that cell is injective. And then we'll define a tiling to be a collection of tiles which are fitting together in a non-overlapping way to cover the amplitude. So this is going to be our modification of the notion of triangulation of polytope for this setting. Okay, so let me just give you an overview of what we know about tiles. So for m equals 1, they're classified and they essentially correspond to the bounded chambers of this hyperplane arrangement. And now one would like to understand the kind of inequalities bounding these tiles.
Depends on the choice of metric z. Are some Wilson space of parameters with things?
So that the hyperplanes themselves depend on z. Yeah. So the hyperplanes might move based on what z is. The combinatorics is independent.
Independent, yeah.
It's independent in the sense that we've already chosen that we've already forced maximal minors of z to be positive. Yeah. And so that's going to put strong constraints. So like when k equals 2, the fact that the maximal minors are positive is going to mean that that we have hyperplanes that kind of have this kind of cyclic order, and that's going to determine the combinatorics. Okay. All right. So anyway, so in this m equals 1 case, we know everything, and boundaries of tiles are linear. But when m is at least 2, the boundaries of tiles are no longer linear. We do have a classification of them when m equals 2, and when m equals 4, there's not a complete classification of tiles, but there are many tiles coming from this BCFW recurrence. But what's interesting is that while the boundaries of tiles are not linear, they actually can be described by cluster variables in the cluster structure on the Grassmannian. Okay, so we've seen a few references to cluster algebras in a couple other talks without a definition. I'll say a little bit more about the cluster structure soon. Okay, but anyway, so the upshot is that for the amplitude we can describe boundaries of tiles, and only in special cases m equals 1 or k equals 1 do you have linear boundaries. But for higher m and k, what you get is boundaries described by cluster variables. Okay, so let me kind of give a hand-wavy introduction to cluster algebras. So these were defined by Fomin and Zelevinsky around 2000. And they're a class of commutative rings with a remarkable combinatorial structure. They come with some distinguished generators called cluster variables, and the relations are encoded by quivers and quiver mutation. Now there's a more geometric viewpoint initiated by Fock and Gontchoff of cluster varieties. And these are varieties whose coordinate rings are cluster algebras, and they come with many nice torus charts. And the coordinate functions on a given torus are called compatible cluster variables. Okay, and you can think of cluster variables as a kind of generalization of the notion of toric variety. Examples include Grassmannians, flag varieties, and Schubert varieties. So these are varieties which are not toric varieties, but have a cluster structure. And it's very useful to find a cluster structure because there's a bunch of nice general results about them. Okay, so relevant to this talk, the Grassmannian, its coordinate ring has a cluster algebra structure. So the Grassmannian has many nice torus charts whose coordinate functions are cluster variables. And just to say a little bit about this, recall that we have Plücker coordinates for the Grassmannian indexed by k element subsets of 1 through n. Now for the Grassmannian of two planes in n space, the cluster structure is encoded by triangulations of a polygon. So here I have a polygon with 8 vertices, so this is going to have to do with the Grassmannian of two planes in 8 space. And we have a chosen triangulation of this polygon, and I labeled every side and every diagonal of this polygon by a Plücker coordinate corresponding to the endpoints of the arc. And to sort of summarize what the cluster structure means in this picture, we get one cluster torus for every triangulation of the polygon. The cluster variables are exactly the Plücker coordinates labeling the diagonals. These are algebraically independent. And so in particular, two Plücker coordinates are called compatible cluster variables if they label two non-crossing diagonals. Okay, so that was G2N. And this picture, this G2N picture, can be generalized in two ways. One way is to higher Grassmannians. Another way is to like surfaces with marked points. This came up a bit in Sasha's talk the other day. Okay, but now for k greater than 2, the cluster structure on the Grassmannian is much more complicated. And we have, in general, infinitely many cluster variables, including Plücker coordinates, but also higher degree polynomials. Okay, all right, so now I want to give an idea of how the amplituhedron is connected to cluster algebras. So first, since we defined the amplituhedron as the image of the TNN Grassmannian under a certain map, what we'd like to do to be more concrete is to have some kind of coordinates on this Grassmannian where we can talk about the amplituhedron directly. So we need good coordinates. We could, of course, use Plücker coordinates on this Grassmannian, but if you try to do that, you actually get a mess. You get a big mess, and the right thing to do is to use coordinates that take this information of z into account. Okay, all right, so how do we do that? So let's, as before, label our rows of z by z1 through zn. And let's let y be a matrix on this Grassmannian over here. So now, given an m element subset I of 1 through n, which I will think of as giving a collection of rows here, what I'm going to do is I'm going to first create this matrix over here obtained by stacking y. Y is a k by k plus m matrix, together with zi1 through zim. So these are m different rows of this matrix. So in particular, each one is a k plus m vector. And so then we get a k plus m by k plus m matrix, and we can take the determinant. And this is what's called a twistor coordinate, and that's what is denoted by z sub I of y. These are the good coordinates for the amplituhedron, and these take into account this fixed data of z. Okay, and these are really coordinates. These are coordinates on this Grassmannian, and so they can actually be identified with Plücker coordinates and a related Grassmannian. Okay, all right, so these twistor coordinates are the right coordinates to use. And now how is this related to tiles? So we can completely classify tiles for the m equals 2 amplituhedron, and they can be described exactly by inequalities of the form twistor coordinate zi is either positive or negative, where I ranges over some non-crossing diagonals of an n-gon. And so in other words, the boundaries of all m equals 2 tiles are cut out by compatible cluster variables. That's a takeaway from this statement. And something that's a bit curious here is that in the theory of cluster algebras and total positivity, there's many settings where people look at the totally positive part of some object defined by requiring all cluster variables to be strictly positive. This is something a bit different because we're not required, so a tile is not cut out by saying certain cluster variables are positive. Instead, we're saying certain cluster variables must be positive and certain must be negative. Okay. Any questions so far? Okay. And then there's something similar for m equals 4. So we have these BCFW tiles that come out of the BCFW recurrence for scattering amplitudes. And again, the boundaries of each such tile are cut out by compatible cluster variables for the Grassmannian of 4 planes in n-space. And in particular, every tile gets described by specifying that certain cluster variables are positive and certain are negative. But all cluster variables are compatible. And the cluster adjacency conjecture says that the same should be true for every tile of every amplituhedron. So no matter what is m, no matter what z, no matter what's your tile, the boundaries of this tile should always come from certain compatible cluster variables. And this kind of phenomenon had been noticed in a slightly different guise by physicists who were looking at they were looking at things like the BCFW recurrence and the terms that you get out, and they were noticing that if you look in the denominator, the singularities seem to be governed by compatible cluster variables. So this is just the kind of geometric reflection of that observation. Okay, all right, so I said something about tiles, and now I want to talk about tilings, which are ways of putting together tiles in a way to cut up the amplituhedron. Okay, and so the question is, can we find some tiles that we can fit together to tile the amplituhedron? Okay, so we want to define a tiling to be a collection of tiles such that their union equals the whole amplituhedron and the interiors are pairwise disjoint. So this is like our analog of the notion of triangulation of a polytope. Okay, so what can we say? So in a sense, tilings for m equals 2 have been classified. We showed that they were in bijection with certain polyhedral subdivisions of the hypersimplex. And this is a kind of a bizarre result in that this amplituhedron for m equals 2 is 2k dimensional, and this hypersimplex is n-1 dimensional. And for some reason, tilings of the 2k dimensional amplituhedron are in bijection with certain polyhedral subdivisions of this n-1 dimensional polytope. So that's kind of a weird phenomenon. Then for m equals 4, it came from the original paper of Arcani, Hamid, and Trinka that these certain BCFW collections should give a tiling of the amplituhedron. And so the BCFW recurrence, there's many ways to iterate the recurrence, all of which is supposed to give a tiling of the amplituhedron. And in a special case for the standard BCFW collection, Evans, O'Hara, Leclerc, and Tesler proved that you get a tiling. And then together with them and Parisi and Sherman-Bennett, we proved more generally that the conjecture is always true. So all ways of running the BCFW recurrence give rise to a tiling. Okay, and a key idea is to use the connection to cluster variables. Okay, so let me switch gears a tiny bit and talk about numerology. Okay, so tilings have been studied in many special cases. And back when Stephen Karp and I were first looking at this, we compiled a table of numbers. And what we wanted to do was look at all known tilings of the amplituhedron, and for each one, say, well, how many tiles are in the tiling? And okay, of course, in the case where k is 1 and m is 2, the amplituhedron is just an n-gon, and so the number of tiles in a tiling should just be n minus 2. That's the number of triangles in a triangulation of the n-gon. Okay, so this number should be n minus 2. If k is 1 and m is even, then the amplituhedron recovers a cyclic polytope, and it's a kind of famous result that every triangulation of a cyclic polytope of even dimension has the same size. And that size is n minus 1 minus m over 2. Choose m over 2. For m equals 1, this is where you get the cyclic hyperplane arrangement. The number of bounded regions is our number of tiles in the tiling, and that's n minus 1 choose k. And then for m equals 2, there were some sporadic tilings known, and they all had size n minus 2 choose k. And then for m equals 4, all known tilings have this number of tiles, which is the Neriana number, which is a relative of Catalan numbers. Okay, so we were looking at this table of numbers, and we tried to figure out if we could write down the generalization of all of these numbers. And you can do that, and it's this number. So this is a famous number that goes back to Percy and McMahon from, I don't know, late 1800s, I think. So let m of ABC be this triple product. And the observation is that every known tiling of the amplituhedron, when m is even, has cardinality this number, where the three parameters are k, n minus k minus m, and m over 2. Okay, so we call this prediction the magic number conjecture. Okay, and it's kind of a curious observation. Well, so this is consistent with all the results I showed you on the other page. But it's sort of curious because there's symmetries, right? M of ABC is symmetric in A, B, and C. But nothing about the amplituhedron seems to suggest a symmetry in parameters related to the K, N, and M. Okay, but by now one such symmetry is known in the amplituhedron. There is a symmetry that switches K and N minus K minus M. And I think, to be honest, there's probably not a symmetry that switches m over 2 with one of the other two numbers, and it's just a kind of weird coincidence that you get the same numbers. Okay, but I'll mention that this number m of ABC has many, many different combinatorial interpretations. So I've drawn a figure to show 4 of them. So this is where A, B, and C is 2, 4, and 3.
And for odd m?
So for odd m, you can have tilings of different sizes. And that's also, that's true of cyclic polytopes of odd dimension, where you can have triangulations of different sizes. Yeah, so there's a big difference between odd and even m. Okay, now, so what do these numbers count? Well, they count a non-crossing lattice path sitting in a B by C rectangle. Oh, sorry, this is what I've drawn is actually 3 non-crossing lattice paths in a 2 by 4 rectangle. These non-crossing lattice paths can be identified with plane partitions, where in every box you record how many paths are underneath it. Then these plane partitions you can think of as boxes stacked in the corner of a room. And if you do that, if you visualize this kind of three-dimensional picture, you will see a picture like this, which you can also think of as a rhombic tiling. And then these are also in bijection with some kind of perfect matchings in a certain hexagonal lattice. Okay, so anyway, so these numbers are quite interesting.
Is it always integer, or when is it integer?
It's always an integer, yeah. So it's not obvious from the formula m of ABC. Sorry?
Is it integer for any A, B, and C?
Yeah, A, B, and C are non-negative numbers, and this number is an integer. Yeah, it's not too hard to see it's an integer, but it's not obvious from the way I've written it. Yeah. Other questions? Okay. All right. So anyway, so yeah. So just to go back for a second.
There's one question. So in the rhombic tiling, like you're filling this corner with these three rectangles. There are variants of that where you replace rectangles with tableaus, I assume. Something like that.
Oh, so in this rhombic tiling, I would think of we're putting little cubes there, and so you want to replace. What do you want to replace with what?
Maybe their side faces with some tableau or something like that. I'm not sure.
Oh, you mean like label? You mean like label these different rhombi by tableau, or?
I'm not sure. Sorry, I'll think about it.
There are some things like what you suggest. I'm just not sure what flavor you might be thinking of. Yeah. Okay. All right. So yeah. So the summary is that this this m of ABC formula generalizes these numbers here. Okay. All right. So so what can we do? We can prove this theorem when m equals 2. This is the case where in fact your size of the tiling should be n minus 2 choose k. Okay. Now as a sanity check, if k equals 1, the m equals 2 amplitude-hedron is a n-gon. And so the theorem says that all triangulations of an n-gon have size n minus 2 choose 1, which is n minus 2. So this is maybe the most complicated, our proof is maybe the most complicated proof you might ever see that a triangulation of an n-gon has size n minus 2. Of course, you need something more complicated for higher k. Okay, but anyway, so let me just say a tiny bit about the idea of the proof. And let me first sort of tell you, yeah, okay. All right, so first what we did was we classified all possible tiles for the m equals 2 amplitude-hedron. So we sort of characterized exactly which appropriate dimensional cells of the positive Grassmannian map injectively to the amplitude-hedron. So we classified those, and it's completely explicit in terms of some combinatorial objects. Now, let me give you the idea by saying if we could show that every tile of the amplitude-hedron had the same volume, that would imply that the cardinality of every tiling is the same.
It depends on choose of volume element, which is not volume element.
Ah, right. So we basically have the right invariant that is the same for every tile. Yeah, so there's a kind of curious additive invariant that we can associate to every tile. It's an invariant that's related to some kind of Park-Taylor functions from physics, and we show that this quantity is the same for every tile. So by showing that every tile has this same invariant, and we know what the invariant should be for the entire amplitude-hedron, that shows that all tilings have the same size. Okay. Yeah. So anyway, so this is so it's proved for m equals 2, and separately it's also proved for k equals 1 because this is the cyclic polytope case. And I'll just mention that this conjecture is kind of striking because actually almost no polytopes have the property that all of their triangulations have the same size. The only polytope that I know of where all of its triangulations have the same size is even-dimensional cyclic polytopes. So anyway, if anybody happens to know of more examples, I would be curious. Okay, so yeah, so just as a summary, the amplitude-hedron generalizes the positive Grassmannian, it generalizes cyclic polytopes, and also the bounded complex of a cyclic hyperplane arrangement. And while the amplitude-hedron is not a polytope, we can make analogies with polytopes and study the triangulations or tilings. And there are interesting connections to both cluster algebras and also to interesting numerology. So yeah, so I will stop there. Happy birthday. Here's some references.
Questions?
Is there an analog of the Ptolemy groupoid? You know, the one that you take a quadrilateral and then you take and flip the two.
Oh, yes, yes, yes. So the analogy would be cluster exchange relations. Although for higher Grassmannians beyond G2n, it's actually not understood in general. In fact, even for the Grassmannian of 3 planes in n-space, there is only a conjectural classification of cluster variables. So there's definitely not a kind of classification of the exchange relations either.
And does this groupoid play any role in physics?
I mean, probably yes, but let's see. Yeah, I mean, well, in this particular setting, we can give, for a given tile of the amplitude-hedron, we can give multiple descriptions as a semi-algebraic set where we say certain cluster variables have a certain sign. And you can always take those certain cluster variables and do a kind of cluster mutation and get a new collection and then re-describe the same tile using those cluster variables. So in a sense, like, yeah, the mutation relations are coming up and are useful.
Can you say something more about the Park-Taylor?
Yes, yes, yes. It's actually super interesting. So the Park-Taylor. So okay. So if you give me a permutation, so say, so this is a permutation, but actually I only care about it as a kind of cyclic order on the numbers 1 through n. Then we can associate this Park-Taylor function, which is a rational function on the Grassmannian of 2 planes in n-space. And it's going to be 1 divided by these Plücker coordinates p, w1, w2, p, w2, w3, dot, 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 p sub w sub n minus 1, wn, p sub wn, w1. So this is a Park-Taylor function associated to the permutation. And now we have a way, there's a kind of natural decomposition of every tile. So each tile of the m equals 2 amplitude-hedron comes with a decomposition into something called chambers. Each one is labeled by some permutation, and then the Park-Taylor function, of the tile is going to be the sum of the corresponding Park-Taylor factors coming from the chambers. And what's really interesting is that if this is a tile of this amplitude-hedron, this sum equals minus 1 to the k, the Park-Taylor factor of the identity permutation. And we have a kind of explicit description of all the chambers in a given tile, and they come from some kind of circular extensions of a cyclic partial order. So anyway, there's some kind of like very cool and explicit combinatorics. But at the end of the day, this is the invariant that gets associated to every tile. And it's this rational function whose terms look like this.
But those are projective coordinates on the Grassmannian.
Sectional bundle, yeah.
Yeah, but
rational section of some standard
determinant bundle, yeah. So do you understand this goes to write this function on corner of Grassmannian, which has poles when at values of Kluger coordinates, yeah?
Yes.
That's again under some constellations, yeah.
Right, exactly, yeah.
And do you understand correctly that each phase is given by the number of equations which precisely is codimension? The number of these cluster variables which you use is precisely codimension.
Yes. Okay. It's a little bit. It's a little bit subtle. So different tiles for the same. Amplitude-hedron can have different numbers of faces. This is not a contradiction because while the cluster variables are so we have a tile, so nk m of z. This is a subset of gr k comma k plus m, and its tiles are described using cluster variables for gr m comma n. So the tiles get described by cluster variables here. It's really twistor coordinates which can be identified with cluster variables here. But I just wanted to say the number of facets can vary from tile to tile, and there's not a contradiction because of the sort of the fact that it's work.
So I mean this. You have some body, and you define by equations. And so if you take some generic part of some phase, so I believe that you have the number of equations equals to codimension of this.
I can show you an explicit example afterwards that I think might be clarifying. But we're defining but you see what we're doing is we're saying that the tiles are described not by saying some cluster variables vanish, but by saying they have a fixed sign.
Yes.
And so these cluster variables are not cutting down our dimension. We're just it's kind of like being on one side of a hyperplane or not, or the other. Yeah.
Other questions? Oh, okay, let's thank speaker.